Logic.
Hello, thank you so much for having me here. So I think it should be more like in a singular. I'm mostly going to present a proof theoretic approach to epistemic modal logic. But anyway, that's just a small comment. So this is what I'm going to present is kind of what I'm working on right now. I'm a PhD student at Monash University, and this is what I have been starting to work on my PhD. So basically, what I'm going to do is I'm going to make an introduction, keeping on focus on this idea of why do we want a proof theoretic approach for epistemic modal logic, and then I'm going to present a particular system that I have been working on. It is going to be a multi-agent system, and I'm going to present how it works, the basic rules, present a little bit of an example, and then finalize with some conclusions. And hopefully I'm going to be okay with time. Just as a general introduction, I'm pretty sure most of you know what I'm talking about, but just in case, when we talk about epistemic logic, we talk about the formal study of knowledge, another propositional attitude. This is usually presented as a variation of modal logic, making use of the possible world semantics that we have for modal logic. And in this context, what we do is basically we supplement the language of propositional logic with a model operator of knowledge K, where we have KA phi is read as agent A knows phi. So normally a model for epistemic modal logic is a tuple of a set of possible worlds, an accessibility relation based on agents, and an atomic valuation function. So in this context, a proposition agent A knows phi is true in a world, if in all possible worlds that are epistemically accessible to them, it is the case that phi. So what happens with this possible worlds approach to epistemic modal logic? When we put the focus on information, we are talking about information as a range of possibilities that the agent consider, where when we have a bigger range in place, that the agent actually has less information about the actual world. Why? Because the agent is considering different possibilities for how the world is. So in this sense, the main focus when we deal with information in this approach is not the actual information, but rather the uncertainty that the agent has. So when we're dealing with proof theoretical side, the usual approach to present epistemic modal logic is in terms of an axiomatic system. And if we think about from the information perspective, the information is given by a set of formulas, and agent knowledge is represented by the set of known formulas. So this can be argued that it's more natural to the way we actually see information outside a specific formal system. It is more natural to the way information works. But also there is there is another disadvantage about dealing epistemic situation in model approaches is that it forces us to pick a model. Well, we can argue that for many situations that we want to model, we actually have partial descriptions that it can't be adequately specified by a single model. Although in many situations this isn't a problem, there are incomplete scenarios for epistemic logic, for epistemic situations are not an exception to the rule. They actually happen a lot. So having a proof theoretic approach has this advantage of it's not forcing us to decide how we are going to model, to decide a model for that situation. So in particular, what I'm going to do in this talk, I'm going to provide an alternative proof system to epistemic logic, which is based on the work of Gavai and Olivetti, which are a goal-oriented system. Main thinking about two main reasons. First, from an information perspective, it gives us a little bit more information because what we are going to be dealing with is with labels formulas. So in the proof system, we are going to have information about the states. And also, one of the motivations that I have to explore this type of system is that I was trying to capture this idea that when we are actually engaging in a proof, sometimes we work our way presenting our premises and then we work from the premises to the conclusion, but that's not the only way we conduct mental proofs. Sometimes our mental proofs are conducted thinking about what we actually want to prove and working our way on how to prove this. So the way Cavallo and Olivetti presented this system to work as an intermediate between what the authors calls a human-oriented system and what they present as a programming paradigm. So human-oriented systems are this idea of all proof systems that are easy for a human to read and understand and see what is happening, which of course, sequence, natural deduction, all of these are human-oriented. And where we, on the programming paradigm, we have, this is not the main focus. The focus is for the program to be efficient, all those type of things. So since they are looking for a system that works as an intermediate between these two ideas, some of the distinctive elements of the system come from the programming paradigm. But they are trying to, they are trying to maintain human-oriented approach. That is, to maintain an understanding on how the system actually works. So, how the system actually works. We are going to have two basic elements in the system. We are going to have a set of implicational formulas, consider the database gamma. So this is important, and this comes from the programming paradigm. All our formulas are going to be implicational formulas. And then we are going to have a specific formula for which we want to know whether it follows or not from the database, which is the goal A. So the core concept of this proof system is going to be a query, which is basically this question of, does A follows from the database gamma, represented by this hammer with question mark. The shape of the goal, the shape of this formula, is going to determine how the deduction process continues. We are going to start with an initial query, and we are going to decompose the goal to its atomic component. If we have those atomic components in the database, we say that the query succeeds. So this can be thought about like a type of tree proof. So some of the rules of the system is going to enable us to open branches into the proof. And if we reach to an atomic component on all of these branches that is in the database, then we say that the query succeeds. What that means is that we can actually answer, yes, the formula A does follows from the database. So how are the rules in this basic system? We're going to have, again, an implicational language, and we're going to have some basic rules that are going to be modified for my approach, but it's nice to see to understand how the system works. So the first rule is the rule of success that is telling us that if we have an atomic formula and that for atomic formula is in the database, that query succeeds. Then we have an implication rule that if we have an implicational formula, what we can do is we can push the antecedent into the database and ask for the consequence instead. And then we have our reduction rule, which is kind of like it does a lot of the magic of the system, which is that if we are asking for an atomic query that doesn't immediately succeed, but we have an implicational formula in the database that has this atomic formula in the last consequence, what we can do instead is ask for each of the antecedents instead. So all the implicational formulas are distributed to this side. So So what we do is we ask for each antecedent. So this is the case where we are actually opening branches. And then, so if with these three rules, the author shows that we have a complete and a sound and complete proof system for intuitionistic logic. If we add the rule of restart, what we have is a sound and complete system for classical logic, where the rule of restart, we have this new concept that is we are going to have a history of past atomic goals on the side of the goal. And we are going to have our query will now have a database, the goal, and a history. And if we have an atomic formula in our history and we are asking for another atomic formula that doesn't immediately succeed, what we can do is go back and ask for this atomic A again, basically. That's what restart is doing. It allows you to ask for a past atomic goal. So with this restart rule, we have a sound and complete proof system for classical logic. So what I have done is I have taken this basic system. They do work on extended this system for modal logic. But what I have done is take this system, this modalized system, and apply it to first talk about epistemic logic, and second talk about multi-agent epistemic logic. So this will involve having a lot of transformations on how we deal with all these elements from the system. So first, we are going to have an extended multi-agent modal language where we are going to have the set of atomic variables plus top and bottom, and we're going to have a set of agents. And a formula of the language implication, strict implication A, an implication is a finite set of formulas built from the set of atomic formulas and the binary connective, the strict implication regarding to an agent, and the implication. So the strict implication is going to be a primitive notion instead of the usual strict implication. Agent A knows that if P, then Q. So why are we talking about a formula being a finite set of formulas? Because that is the way we are going to interpret conjunction. And because I want to apply this as naturally as I can to an epistemic modal setting, I'm trying to have in my language our usual connectives, of course. So we are not going to work with any formula of this language. We are going to work with a particular subset of formulas in normal form, which in a particular subset of formulas that is called a formula in a normal form. Well, a formula of the language is in normal form. It is if it is an atom or has the form of S0, implication S1, strict implication, and ends in an atomic formula. So basically, the thing is, we need to have this first material implication here and then follow with the strict implication. I cannot have, this is the main thing we need to have in this normal form. Why do I want to focus on this normal form? Because I can prove that this subset of formulas enable us to express every formula of the language containing disjunction, conjunction, K, and negation. I'm not going to go over how this works and the proof, but these normal form formulas enable us to express formulas of that language. So now we are going to have some changes in the database as well. The database will now have two elements. We're going to have a set of labelless implicational formulas, and we are going to have a set of tuples representing the relation between labels with respect to an agent. So this idea is that the labels are states or worlds, basically. And all the formulas are going to be with respect of a label, and we are also going to have in the database the links between those labels with respect to an agent. And we are also going to need an operation over the database that involves an expansion of the database. So we are going to have that the database gamma alpha is going to be expanded with the formula S in I by A and X. And what we are meaning by this is saying, okay, what I'm doing is I'm adding the formula S in the state I, and I'm adding a link with respect to an agent and with respect to a previous label to the database. So this is going to be relevant when we are dealing with a strict implication in our rules. So the relation between the links for each agent is going to be represented by a family of relation symbols, A is alpha, X, Y, A, where A is an agent, X is I, and labels. And where these relation symbols will have some conditions. So for K, we have that if we have the link in our database, then those states are related to each other with respect to an agent. T tell us, give us reflexivity. 4 give us transitivity. 5 give us an Euclidean relation, and B give us a symmetric relation. So the relation predicate must comply the condition K, and according to which other conditions the relation predicate comply, we are going to have different modal systems. So a query in this system will now have the following form. We are going to have a denumerable set of labels. We are going to have a set of agents, and a query in a multi-agent context has the form of delta alpha, which is our database. Query CX, we are always asking for a formula in a certain state, and we also have our history, where now we are not only going to have past atomic goals, but we are also going to have the labels of those past atomic goals. And she, of course, has to be a normal form formula. So we are still asking the same. You're still asking, does the formula she in the label X follows from our database? That's the main thing we're going to work with in this system. So how are going to be the rules for this multi-agent system? First, we're going to have the success rule. It follows the same idea. It will immediately succeed if this atomic formula on that state is in the database, or if the atomic goals is top always succeed. For the rule for a strict implication, what we are going to do is, if we are asking for a strict implication, what we are going with, this is going to have the same idea as the basic rule. What we are going to do is we are going to put the antecedent, we are going to create a new label where we put the antecedent, we assume the antecedent on the database, and we ask for the consequence instead. And this new label is going to be linked with the state where we were asking about this implicational formula. This is important. The label we are adding here has to be completely new. It cannot be in the database, or it cannot be in the history. For the implicational rule, this is the same as the basic case. We put the antecedent on that state on the database, and we ask for the consequent. I'm sorry. We ask for the consequence, but we don't change labels here because we are asking for a material implication. Now, the reduction rule is going to be a little bit more complicated. So we are still going to have, we are asking for an atomic goal, and it doesn't succeed. And we have a formula in our database that has a normal form formula that has this atomic goal as flat consequent. What we are going to do is we are going to start asking by each of the antecedent. The first one, we start from this label Q. So the first one, because this one is a material implication, we ask it we need to keep asking this in labels that are related to X. That's the main thing about this. We ask about each of these antecedents in labels that are related to each other. So in this is very important to know which, of course, which conditions the accessibility predicate comply, because this will parameterize how this reduction rule works. Because of each of these cases, we need to ask for a label that is related with the original one. So the first label we ask is a label E, and the last one is a label X. And because we are in a multi-agent setting, of course, all of these links must be regarding the relevant agent on each step. And I'm going to present an example later, which I'm hoping is going to make it more understandable how this rule works. And then we are going to have our restart rule, where if we have an atomic formula in the history that is in a certain state, then if we are asking for an atomic goal, we can ask instead for this formula that was in the history. And because we also have falsity in falsum in our language, we also have this falsity rule, which tells us that if we are asking for an atomic goal, and we have other, if we have any label in our database, we can ask for falsum in any label of our database. And the final rule is the conjunction rule, because as I said at the beginning, we are dealing with finite sets of formulas, because that's the way we are interpreting conjunction. So if we have a set of formulas as our goal, what we are going to do is ask for each of the formulas. So what we are going to do is we are going to open a bunch of range for each of these formulas. So all of this is going to receive a semantic meaning through the notion of realization. A realization is going to be a function that let AS alpha be an accessible predicate. We have our database, we have our set of agents, and we are going to have a predicate models that have set of worlds, accessibility relation regarding agent, and evaluation function. What we are going to have is a map that relates each label to a world from the model. This map is going to be called a realization of the database in the model with respect to the accessibility predicate if the following holds. If we have two links regarding an agent in our in the scope of our accessibility predicate, we are going to have those labels related, the worlds that map this, the world that are mapped with these labels related also, we're basically saying the relation holds for the model. And we also have, if we have a formula in a certain world in the database, then the model is going, that formula is going to be true in the model in that particular world, the particular world that is mapped by the function. So these two things has to hold to have a realization. And that is the way we are going to give a semantic meaning to the queries. So now we can talk about validity. We say that a query in this proof system is valid in S, being S any modal logic, if for every S model M and every realization function of the database, we have either that the goal holds is true in the model in that world, or for some goal in our history, that goal holds in the world. This is, of course, because we have the restart rule. So with this notion of realization and validity, we can prove soundness and completeness for the system. It's something that I have been working on mostly last year, and I have completed the proof. So this system is sound and complete. So that's good. So basically, this is the whole idea of how the system actually works. So now I was thinking about, well, how to apply this to a context that is relevant to be dealing with epistemic modal logic in a multi-agent setting. So I thought about, okay, let's think about this for a classic epistemic example, which is the muddy children case. So let's think about how we apply this proof system to a muddy children case. So what is the classic muddy children situation? I'm going to keep it simple. We're going to consider only two children who meet their father after playing in the mud. They know they can enter the house if they are mud, so that's relevant information for them. They don't want to have mud on their face, but while they were playing, some of them become muddy. So the father says, at least one of you have mud on her forehead. Then he proceeds to ask several times, does any one of you know whether they have mud on her forehead? So while I was trying to think about how to use this system to model this situation, because of all this system is constructed in an implicational language, I was trying to think about, okay, how do we put the information the children have in this implicational approach? So one of the things that each children knows is that if they don't have mud on their head, the older child knows for sure that they have mud on their forehead. Why? Because we are assuming that the father always tells the truth, and the father has told that some of you have mud on their forehead. So let's consider we have two agents in our set of agents. We have child 1 or child 2. And let's consider we are representing this information as M1, child 1. Let's consider the formula M1, child 1 has mud on her forehead, and M2, child 2 has mud on her forehead. Our initial database will consist of one label and two normal form formulas that are going to be equivalent of this information that child 1 knows that if they don't have mud on their forehead, then the other child knows they have mud on their forehead. And the same happens for the other child. So we only have these two formulas, which are going to be put in normal form. Two agents, and we only have one label. But what we are going to work on is we are going to put conditions on the accessibility predicate that we're going to have K. Of course, that's the basic that we need to comply. And we also have reflexivity. So with that information, any query about whether a child has mud on their forehead or whether they know if they have mud on their forehead is going to fail, which is, of course, what we want. But what happens when the father asks the question and both children answer truthful that they don't know? So our database in the second instance is enriched with this formula that child know, that child 2 doesn't know that if they have mud on their forehead, and the same for the other children. So this is the way we are going to have our database now. So this is our normal form formulas. So we are going to have we are representing negations with a conditional with falsium. We are representing knowledge with strict conditionals that goes to top. But anyway, this is how we are going to put the formulas in our normal form. So this is this express the same of the formulas. These two, of course, are these two formulas, and these two are these two. And since we only have one label, what we do have reflexivity in our system, what we are going to have is that XX, we have the link between X with regard of each child. So what happens now? In this scenario, if we ask the query, does child 1 has mud on her face, that query is going to succeed. Basically, we start with our initial goal. We're asking for M1 with our database, and then we can apply reduction rule with respect to these formulas. So this is what I have been, because we only have one label in our database, but that label is actually linked. Because of reflexivity, we can apply reduction and ask for each of our antecedents in the same rule. This branch, of course, succeeds because it's top. And this one, I can apply the material implication rule. And we put M2 to our database, and we ask for falsum instead. But from falsum, we can apply reduction again from this formula. And we are going to ask for top here, which of course immediately succeeds. And this one, of course, also succeeds. Why? Because we add it to the database. So this query succeeds, and that's, of course, desirable. Also, if we ask, does the child one knows they have had, if they have mood on their forehead, it's the same. It's going to succeed. So one thing I was, while thinking about this example, and the reason why I chose to ask, does the child one has mood on her face as an example to present, is because it's kind of like we can think about this about try to think about the process of, can the child ask herself this question instead of asking about knowledge, but it will succeed again. So some conclusions. I have presented this extended goal-oriented proof for epistemic multi-agent settings, where we start asking whether a goal follows from a database, and we have that certain goals and formulas will be relative to a certain agent and the states that that agent access. And of course, every goal is going to be regarding a particular state. But I think this particular type of system can be quite interesting to work on, is because since we have a label proof system, we actually have more information in the system. We have information about in which states those formulas hold. And also because especially how we construct the notion of realization and how we construct this system, we are not forced to pick a model to work with the epistemic situation. Of course, in the moody children case, to pick a model is not really problematic. But in some epistemic situation, especially in some game situation, it's not desirable to actually pick a model when you're dealing with that situation. So I think I rushed a little bit through. This is all I have to talk about. Thank you very much, and thank you very much for this opportunity.
Oh, thanks, Alba. All right, people have questions.